functions, will the input arguments, does it always go in like in order left to right, register 0, 1, and so on? Or is it depending on like what the data is or what the function is?
We'll talk about that today. That will be in today's lecture. Yeah.
Is there any chance we can get like an ARM instruction sheet? Because right now, like it's kind of annoying going through the entire manual.
Welcome to being an engineer.
I know it exists. Yeah, I know for a fact it exists.
I know you have.
We can give you the one that we'll give out in the exam. I'll take a note. But like, that's the life of an engineer, man. Like, there's a search function. You can search through the thing.
If I need the specifics, I'll look it up. Like just the instruction, like
what are you looking for? Give me an example.
I'm not doing.
sheet that has every instruction available in ARM v7. And then like.
Okay. We'll post the we'll give you an exam. It does not have every instruction, but it'll have what you need, and usually the slides have what you need. But we'll make a one source for you. That's a good.
That's how I thought. We don't need to. Yeah.
Yeah.
My laptop doesn't have enough RAM.
Like I can't. You got a Mac. How can you not have enough RAM for a PDF?
It's 8 gigabytes of RAM. If you have Chrome open, that's like.
All right. I can only put things on the web. I can't solve you have not enough RAM. All right. Any other lab problems before we get started? Or questions? Logistics questions? All right. Homework 2 is posted. I don't know why these are out of order, but it will be due Monday next week. Okay. Homework 1 was due yesterday. We do give one late day. You get 10% penalty. The goal is so that we don't have to have small issues, right? I was 5 minutes late. Please let me submit my homework. I don't want those emails. You don't want to write those emails. That's why there's a 10% penalty for whatever reason. I don't care. You're late by a day. There you go. And of course, if you have a medical emergency or there's something that's beyond the scope of normal class, let us know. The expo times and dates have been set. Somebody asked about that. I think it's up on the website now as well. So it's the last day of class. That's a Monday. I realize that this is starts before class, right? So at least one of your partners should probably be there to demo, even though it starts a half an hour early. Setup will be about 11 a.m. and then we'll break everything down by 4 p.m. But during those hours, you should at least have somebody there demoing your project. Okay? And this would just be in the EECS building. Any questions? Great. All right, I want to talk about components of the day. So batteries. It's pretty simple. A lot of people use batteries every day, but there's a few small things to keep track of. One, let's see. So when we talk about nickel metal hydride, these are normal like AA batteries, like what you have in your remote controls. They're about 1.5 volts. They vary. They have this discharge curve, and it's important to kind of realize that as you pour more current, the voltage actually droops. And so that's the common discharge curve for a 1.5 volt battery. They're very low cost, really reliable, easy to charge. Then we have newer chemistries, so lithium ion, lithium lipo, there's a lot of lithium something batteries, there's about 12 different versions. High energy density, but they're very sensitive to overcurrent and over voltage. So these are the ones that catch on fire really easily. And so you have to be careful with them. And you'll notice here that the voltages are not in nice increments, right? So it's like 1 volt or 1.5 volts to maybe 1 volt, that's the range. But when they say a 3.4 volt cell, they really mean at fully charged, it goes up to 4.2 volts. And then it will discharge, and it'll be kind of constant for a while, but then it's probably usable down to 3.3 volts. So batteries are not a regulated source. If you're going to use them in your project, you're going to need a regulator or something to make it so it's not varying all over the place, or else your electronics may run in a weird way. You can stack cells on top of each other to get higher and higher voltage. That's fine, but you're still going to be in one of these increments of either 4.2 or 3.4 volt cell, or maybe if you're going to use nickel metal hydride, you'll be in 1.5 volt land steps. So the idea here is that your electronics, like your dev kit, that's 3.3 volts. It's not going to tolerate any more than maybe 3.6 volts. So you might, when it comes to project time, you're going to have to figure out, how do I take this world of these discrete values of batteries and deal with what the requirements of the device manufacturers are, and you have to figure out how to do all your power management. We'll help you with that, just have to be aware that this is a challenge. Any questions? How many people kind of knew this already? Okay, so maybe I'm teaching you something that's useful. Okay. Yeah.
So like, if you like mess up with your like on the project and like your component breaks, like how bad is it?
Like if on demo day you have nothing to demo?
No, not on demo day, but it's just like you're just building it and then just like something kind of like expensive breaks.
Well, I mean, this is part of the project. Is not like everything you've done up until now. There's like a homework set in the back of the book, and it was very safe, and we knew you could figure out the answer. That's not this class. Right? This is more like real world. And so we're going to give you a project, and you're going to have to make trade-offs. You're going to have risks. You're going to have goals you're trying to meet, and all you're trying to do is get something that works at the end of the day. So you can see how risky you would be by doing certain weird battery configurations. If something breaks, you should have planned to have an alternative. If you have like one component on the entire planet that you need, you might be screwed. Or you might say, oh, it's a 2-week lead time for this part. You should have probably gotten 2 in case you mess up, right? So you have to do this kind of planning to make sure that you still deliver something successfully at the end of the project. Does that kind of answer your questions?
Yeah.
Does it make you feel any better? No?
No.
It's like, this class sounds horrible. But we'll help you. That's our job, because we've seen electronics fail a whole bunch of times. So we'll make sure that you are set up in a position where you're likely to have a good outcome. We won't let you buy like one part, and that's vital for your whole project working.
Electronics breaking often?
Yeah, look at all these young people here with never using electronics and throwing them on the ground or overheating them. It happens, yeah. That's fine. We know it. Okay. A few safety guidelines for batteries. It's not always obvious. You can't actually solder batteries. So nickel metal hydride, any batteries, if it gets hot enough, it'll explode. So I had a buddy of mine when I was in college, and he was doing a robotics project, and he like just literally soldered like a 12 cell battery, nickel metal hydride, blew up all over him. He had acid all over his clothes, run into the bathroom, right? It's not what you do. You don't solder them. They're welded. We don't have the welding equipment. Your guys aren't going to do that. You're just going to have normal batteries, and you have to use mechanical like clips or something to make battery packs. We'll give you that stuff, but never solder anything. This would be considered a battery cell bare. These are extremely dangerous because they don't have over voltage, over current protection on them. So if you short them out, they'll just burn. Okay? What you need is something like this. Most batteries have them, which is a over current protection, sometimes over voltage protection too, which it will disconnect itself, the battery, from the circuit if it gets over voltage. So you need to have that. That's why we don't have you ever use these in lab, because you'll burn down the lab. This is more likely what you would get, something with a connector already, foil, and here's the battery over voltage protection and over current protection. So you need to have that. In lab, you should never solder batteries. What else? Oh, don't do what my graduate student did, the one we talked about in Zurich. She would go through, and because there's nobody there to mentor her, so she'd go and put a new connector on. She just cut both of them at the same time. Right? You have metal cutters, cut through both of them, sparks come out, great. Sometimes it would short out. You just got to be super careful. So I always like cut one, put tape over it, cut the other one, prepare. Think about like all the things that could go wrong. Ask us for help, we'll help you out. Lastly, lithium-ion batteries are very sensitive to over voltage and over current. This is why, if you remember, when the Boeing 777 came out, there was all these news reports about batteries burning, exploding in the cockpit or somewhere in the cabin. It was because they didn't have good thermal management, so you have to be careful. All right, any questions? Okay. On to the last lecture, we talked about register maps, or memory layout, register maps, and instructions. We didn't get to a memory example. If we have time today, we'll do that. Today, we're going to talk about assembly programming tools, the tool chains, and then we're going to talk about the application binary interface, which allows us to call functions and use stack pointers. Okay. So you guys are pretty used to working in C, right? It's a high-level programming language. We've extracted a lot of the details away. We use a compiler to make assembly, but assembly is not what actually runs on your chip. You need an assembler, which takes this code and turns it into machine language, right? So ones and zeros, and figures out where to put them in the memory map. So it's called floor planning. And it figures out, okay, well, this is the beginning of the program and where all the functions come together. Most of this is abstracted away from you. So you're using CubeIDE for better or for worse, right? This is, some of this is GUI based, but a lot of that is abstracted away from you. But it's important to kind of know that there's something underneath. So if you look at what are all the ARM development tools, so there's a lot of them in the world, usually specific to different chips or chip vendors, and they have a few things in common. So most of them run on GNU GCC, which is an open source set of tools for making computers work. So particularly microcontrollers is one of the things they do. And basically, there's just not that many people in the world developing the nuts and bolts. Like, how do I take a program and literally put it on the chip so that it actually runs? And so there's open source community, and all these vendors build their tools on top of it. So if you ever find yourself needing the lowest level control and access, you can go look up the core GCC GNU tool sets and use those to manipulate. I had a student where we were trying to do energy harvesting debugging. So we had energy harvesters that ran on RF power, and they would reset like 30 times a second because they'd run out of power. It's fine, but they're always in the world trying to do something. And the challenge is, if you try to use your debugger to understand what's happening inside of it, that debugger would put power into it. So all your bugs would go away. So you might have a bug that says, oh, I turned on, I tried to do these memory access things, I tried to measure the sensor, and then I just crashed. Well, why? But if you measure it, it wouldn't work. So the student knew GCC really well and made his own debugger, so used the open source debugger and made a zero power interface, so a piece of hardware that would go into the thing, not inject any power, set up breakpoints and memory address things so we could manipulate the microcontroller while it was wirelessly powered. It was great research. I didn't even know it was possible. He exposed all the world of what you could actually do with GCC to me, so it was great. Anyways, you just need to know there's a bigger world underneath there if you ever need it. So the GNU chain, here's just some pointers if you ever need it. There's compilers, there's binary utilities. This is the GDB debugger that we used, some standard sets of libraries. This tool chain looks something like this, and it's good to kind of know how all this is put together so that you understand what files are being output of CubeIDE. So we have C files, you have assembly files, object files, assembly gets turned into objects, you have libraries, and then you have your GCC compiler. This can use this linker, sometimes we call it a makefile, which will take all these files and turn them into something, right? Into an executable that has, this is where the beginning of the program is, this is where data goes, like literally like telling which memory address, right? That's the job of the linker, to figure all that out. And then you come out with an executable, and there's two different copies. There's the bin, and then there's the list file. And this is for debugging. This helps your debugger understand what's inside of this thing. The binary is what goes into flash on your microcontroller and actually gets deployed. The disassembled code is what you will step through if you're stepping through your code. You're looking through the assembled code, and your debugger is looking at your disassembled and your binary working together through JTAG to walk through the code as it's working. So it's just good to know that this tool flow exists for your microcontrollers. Yeah.
Like the C files, that goes into the compiler with GCC, like they also produce their own O files, right?
Correct.
And they come back over there.
Yes, it's just, we did miss that step, but let's just say that your C files get turned into .o files, and then all the .o files get placed into memory, get assembled. All your labels get resolved, all that sort of stuff, and then you come out with your executable image. Any other questions? Okay, so let's look through an example of a program that you could potentially see. So this would be a complete program in assembly. And remember, the assembler has to turn it into binary. So there's some helper functions, essentially. They're called directives. This tells the assembler what to do. So global.space is make this a publicly variable. Let's see, actually I have examples. These are labels. Labels are places in memory where you will go to. So they're kind of like a marker, and they'll get, when the assembler goes through, it will be placed at a particular location, and it will know that you have to go to that memory location for, say, your branching functions. And then you have your core code. So let's go through, we'll go through one by one. So I got ahead of myself. So this is globally exposed, the symbol start. You have their directives. So there's space and data. So let's look at that. So there's the GNU assembler manual. I don't actually expect you guys to go look it up. Just knowing that these things exist are the important part right now. Space is going to go through and give extra zeros. It's going to fill up a part of memory. Okay? And then byte is a method that allows you to take data and place it at particular locations in memory. So byte here is a 0, or let's say expression separated by commas. Each expression is assembled into the next available byte. So wherever byte occurs, you're going to go put down the data. In this case, byte, you're going to put down these values in sequential locations in memory. We have move. Oh, this is, you guys loved this last time. Let's see if I can get this part of the lecture right. So we have move, move wide, and move top. So we got move wide. Move wide is just a move function, okay? Don't worry about move top right now. Move wide, all it does is going to take 16 bits, because that's all that can fit in the instructions, and place it into memory, or into a register. So it's a way to get an immediate into register. But because you haven't defined the upper 16 bits, is this going to make those all zeros? Okay, just define what it does. Somebody did ask me about constants, and I got that wrong. There are constants, but not like constant 0. Okay? Constants work as a version of the T2 encoding where you can say, I'm going to take 4 bits or 8 bits, and I'm going to place them at one of these locations. So you can make large numbers. Is possible. You just don't get full flexibility over each individual bit. So constants, not like you get a 0 or 1. Constants, like you can make a value and then place it into one of these binary bins. So this can go here, here, here. Don't worry, that's not on a test. Somebody asked me, and I forgot about that. All right, move top. So this was this specialty function. They're trying to make it easy for you to get full words into registers, okay? So they're going to give you move to put the bottom 16 in, move top puts the top 16 in, but does not affect the bottom 16 of whatever's in that register. How do you feel about that today? Yeah.
Sign extend.
Is it sign extended? No, you're just telling it what numbers, what values you sign extended. Yeah, your assembler will do sign extend, yeah.
Like if we, let's say we add the top 16-bit 111. -1.
-1, yes, he'll give you all F.
We'll give you all.
Yep. I wasn't, yeah.
That's why I've seen when you're loading a 32-bit word, you move wide the lower 16 bits and then move top the upper 16 bits, as opposed to just doing the full thing in one step.
Because move W is not the inverse of move top. That's why. Move W will always put zeros on the top. That's just how it is. Don't know why? It's telling you how it is. Okay? Move top will do not cares on the bottom 16, which will preserve whatever is putting in that register. It's going to give you the top 16 and leave whatever is in the bottom 16. So they're not symmetrical functions. Yeah.
Is there any move function that ignores the top 16 bits?
Not that I know of.
What is like
Just move MOV do then that's different than move W?
So you can go look through, let's see, move. If we look here, you could move an 8-bit immediate, okay? But that's not gonna, in this particular example, we're trying to get a 32-bit value in that register. So if you didn't care, if you wanted the tops, the full 16, you could use that encoding. The W just, in all things, defines that it should be the wide version, should be the 32-bit. So you'll see the .w, or just the W, as a potential suffix in lots of encodings. And it tells the assembler, I expect you to use a 32-bit no matter what. Yeah.
Is it possible to move a 32-bit immediate value, or is it like not possible because? There aren't enough bits for this.
It's not possible because there's not enough bits. It's not possible to do an arbitrary 32-bit value, okay? But as I reminded myself after lecture, you can get a 32-bit value if you are willing to have a bunch of the trailing zeros or trailing numbers to be all zeros. So this doesn't really solve the problem of putting arbitrary 32-bit values. It just gives you an option of saying I could do, A, B, C, D, blah, 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 0, 0, 0.
So you can move like certain 32-bit values that are encoded.
What it's saying is you can define 8-bit values or however many this is, right? 8-bit values. And then you basically have a logical shift operation that's embedded in this assembly function that allows you to place it over into one of these 8-bit bins. So you could be here, 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 here. Does that make, don't worry about it. Somebody asked me about constants and I was wrong. You can make constants. They're just not the constants that you were thinking of. You can just brain dump this one, yeah.
So let's say you had like an immediate that was larger than 16 bits. And
Yep.
you wanted to use move W then move T to put it all into a register.
Yep.
Does assembly know, like if you gave it the immediate, like what the top 16 bits are? Do you have to give it like a different immediate that corresponds to like what the top 16 bits would be, if that makes sense?
The top is telling it, the move top defines what the top 16 bits are.
Okay.
Move W gives you what the lowest 16 bits are.
So could it take the top, like if you gave it a 32-bit immediate, could it just take the top 16 from that 32 and then it would put it in where you want it? Or do you have to give it a different value?
You can only give it 16-bit values because the instructions can only hold 16-bit values. In assembly, you can try and give it a larger value, but your assembler should throw an error. All right. Let's do any final questions about move W, move top. I mean, you guys can always ask later, but yes.
In the manual, it shows different encodings, like T1, T2.
Yep.
What are we like, what exactly, like, if we're like writing out assembly, what like format would we put it in?
What does your compiler try to do? What's your compiler's goal? Or your assembler's goal?
Convert it to machine code?
But it's got to optimize for something. Does it optimize for largest code size? Right? It's trying to optimize for smallest code size while still giving you the functionality. So if you had to, on an exam, I gave you an evil, tell me the encoding of this thing problem, the best thing to do is try and get the functionality you need in the smallest code size. But you got to hit the functionality first. Some of these instructions you just can't get into a small, like you can't get a 16-bit immediate into a 16-bit instructions. It's not possible. Does that answer your question?
For the immediates, are they like concatenated with each other eventually?
You mean like
For the second
here,
encoding?
here, and here?
For the third encoding and the second encoding.
Right, so it tells you approximately what the concatenation is going to be. And it's not necessarily that it goes in this order, which is awesome. Yes?
Question on the homework one that kind of involved that. So is encoding like automatic in the sense of like the compiler optimizes? But
Yeah.
Like I know that on the homework there's a question that I don't remember exactly which one, but instead of using 16-bit, you have to use the next encoder, 32-bit. So it just you don't have to specify anything. You just do the command as.
Your assembler should optimize for code size. You can give it you can tell it, I really want you to use the wide command. I don't know why they do this. So you could say move wide. You could say add W. And that would force it to use a 32-bit command. Not sure why you'd want to, but they give the assembler, I'm sure somebody figured out a reason. The assembler has that option or the compiler has that option. Okay. Don't worry. We're not going to go that hard into move in this class. So you guys know all you need to know, I promise. You just move W, does a 32-bit word, takes a 16-bit value, puts in lower 16 zeros on top. Move T only moves the 16-bit to the top, leaving the bottom 16. That's all I got to know. Promise. All right. We have these directives here. These directives are saying that we have data. Data's up there, and we're going to take the lower 16 bits of data, and that is going to be the value that goes into move W. And then we have the upper 16 of data is going to go into move top and go into R1. Okay, so those are just directives. If you had to, you could go look them up in the manual and see what they do. Basically, it's just a way. Data is a memory location. So it basically points to that and says, give me the upper 16, give me the lower, or the lower 16, upper 16. Okay, it's just another method for getting data into your registers. All right, we talked about load. We have load byte here. This is a reminder, we have load byte register, load sign byte. So these are both commands that allow you to take data from memory, put it into a register. What's the difference between load byte and load sign byte?
Sign extension.
Sign extension. Now, why does that not matter when you're doing store? You remember? Yeah.
Because we only care about like interpreting it through a sign extended notion, and by like we're putting stuff into like memory, we don't really care about how we put it.
Exactly. It's not at this lowest level. That's not what. There's no sense in saying byte extend a sign. If you're just putting a byte in, then sign extend the rest of it. It doesn't exist, right? There's no data up there. It's only doing 8 bits, and then another memory address. So you can't 8-bit store sign extended. Doesn't make sense. It's not useful, at least. Okay. So what are we at? Then we have compare. Talked about this last time. Compare just looks at 2 values and tells you if these are equal or whatever the ALU is going to put out output. There's no output of this command. So what happens when you run this command? What gets set? Yep. And then we have branch. This is, remember the branch commands, or this immediates and branch. So the branch command here, remember we had all these conditionals we can put on the back of commands if we want. And so we can just say branch. It's not a whole separate command. It's just branch and then do branch if not equal. And then loop just tells you to come back up to that place in your code. All right. So in this class, we have worksheets because it's exciting. So when you guys work together and tell us the values of working groups, put your name on it as part of class participation. I'm back trying to figure out what R0, R2, R4 are.
How do I store it?
It's just like you're telling it that these bytes are there. So we're saying
Gotta try Ticonderoga next time.
We split a group like when he puts data, see the lower 16 data.
No, I haven't. I still have it.
Lower 16 is what's the number?
Really bad.
it's saying like 0, 1, 2 is
Yeah, whatever you have.
so we don't know. All of this.
R0 and R2 start with
This is like one number. Just some of them are 132. This is 132-bit number, I guess. This is 132-bit number. This is
The end is the limit. I don't know what's backwards anymore.
that group is doing is moving that number and that white things I'm confused as to how a group has a load like.
Will it just be this half?
This is the yeah.
This isn't hex.
I'm confused. How are we supposed to know what's in this?
I guess it's confidence if we're gonna.
You have to always remember which way memory is going, which way is the memory index. So sometimes memory index is going down, and that's this way for Little Indian, and then sometimes memory going up, and it's this way for Little Indian.
Each expression.
I believe. Just all you have to do is just state on your statement, I assume this is Little Indian, or I assumed in Indian, and then it's fine.
I'm not sure which one is which.
Like, cause you started at address 00.
Like, I don't think it necessarily matters.
A location of memory.
Yeah, because like even here, when you reference it, it's just lower 16.
Question from lecture that you have something else confused about I was wondering if I could have one. So for one of them,
Yeah. What's negative one?
but then I guess my question was like, I was looking
By the end of
So the lower 16
Or immediate.
or 1,
Or register.
-1 would bits.
Right.
Good, and there says it's a constant, which is I think what we're talking about earlier, says left. 2 is gonna be equal to, I don't understand, like
Register first data, then you can also
address. I lost the page, but I was having trouble understanding like what the range of constants is and what I could do what.
second one is
Address of R1 is some, I can't see that.
it's looking for the address and saying
I think so, I'm not sure what the endian is.
R4 is good to
Plus R2 in our big endian.
find what R1 is.
Right, but I'm also not sure which part of data.
Because I don't know what it is.
Something from that memory location.
It doesn't even say.
What we're saying here is that
Oh, no, it's a loop.
so we're gonna move 0 to there, we're gonna move 0 to there, we're gonna move
That's what I'm saying, I think we're interpreting byte.
not the actual data.
Address. Well, it's gonna get the data in memory.
So
I don't think it matters unless we just have to be producing a series of addresses.
How's it going?
This is so special.
Yeah, it is.
So are they just like, it's not dereference data, it's 12, 14, 21.
So now R4 is 20.
It's 1 byte, right? That makes sense.
That would
Just
location. Okay. You can
So R1 should get the value 0x20ff.
He just gets, it's always gonna be 20 at R.
Upper,
I
yeah.
fucked up with how many bits are in two.
What term is that?
R4 is just 0.
Yeah.
I think R4 is.
This doesn't even matter. This doesn't even matter.
So is byte?
3 is, yeah, that's a host.
So
Because this subset location. Yeah, the R was there, so
Okay, that makes more sense.
There that's what's 4, and the loop ends if it's equal to 4.
that steps over to a higher memory address, with a higher memory address to the higher memory address.
So if we're doing little endian,
Because the add is before the compute.
Say it's the memory add.
would R be R1 address, like
Because it's using that as an address now to index the memory.
20 we store R2.
This command now.
explain it. So R1.
Then you add R2. Value of R0
Store the value of R2.
Spaces after the space.
We never change R1. R2 be
when you put lower 16 data, why R1 is this address? Okay, so
Sequentially. So,
some address.
okay, thanks. Memory location. And it steps to the next memory location, puts a byte down. Steps to the next memory location, puts a byte down.
Start by looking at OX12, and then the next one we go to 20.
0x.
Yeah, okay. And so when you do lower 16 data, it's taking the address. You add 1 to R0.
Times whatever is in the memory location.
Sign extended.
Memory location.
What is what's the value here? What's going in here? Is this an address in R1?
R1 is the address of the data section, so then R2 loads in the bytes of the data
Right,
section.
it's getting the upper of the label, although in directives don't necessarily have labels of data. Wherever that is giving you, here's the address of where that location is, where that memory is going to be.
Just the 20. So you do is just worry about taking the 20.
Know what it is. Well, you could figure it out.
It's the most significant.
R0 is to 0, and then extend everything you get, so then it goes to 0.
Because you add 9 extended or 0? Yeah.
And this is loaded. R1 at R1, the first, the lowest button, which is 12.
Go up again. Might not see that. That's totally fine. We just know that there's data of data happens to be good.
Oh, I think like if this is oh, this is post order.
Oh, because you're taking the first one?
That's with the it should be 1 2. It should be 1 2.
Right. It's going to be OXFM. What happens when you do this on a negative?
Okay, so what did you do here? You took, this is the address, right?
It's a sign extended version.
It's the equal flag. So then
Backwards, but it'll be.
When the least significant bit's the lowest, part of the reason I'm thinking is, or most significant bit's the lowest, you have it turn to 13.
This the data.
So it's just going to go to the address.
They both say that they sign extended.
Because it matters to take the byte from the beginning and the end.
Final values, I think.
Negative 1 will be this. It'll be negative 1's all ones, right?
It should
No,
be.
it's 1 ones, right?
So.
R1 is negative plus the max positive, basically.
Load register.
0 and 0, 1, 1. You're gonna load in another. It's the number of times you loop. So it's gonna loop. It's gonna loop 4 times.
So the
That's what I was saying.
12.
yeah, then you go to your
Do 1 2.
or
The spaces.
that's just you never.
Yes. So
It's that negative 1. It's really
R1 is pointing to
then your R2 is now pointing to 20.
then a plus 1, right?
4
is now equal to. You're gonna keep your register values in this one.
R4 is
Then R0.
This is just loading.
I'm gonna keep my register values in hex, so it's all consistent.
significant. And then it writes to
then R2 becomes X.
It's on loop. It takes the next one. Yeah. Wait.
That's R0 and it's 4. Yes. So then you I just said type on also. This is roughly not equal. You get negative 20.
Now you're adding X.
Our data is gonna be, say start at 0, gonna keep it decimal. R0 is gonna end with, gonna look here first. First,
And R4
0x12 plus 0x.
Double check X 26.
20 plus -1 is 19, I know that.
Then you increment it one more, so now like R0 is 2.
Plus 19.
They like made it more stuff issues, I guess.
What if that means 0? That means 0 if you're taking decimal, which in hex is.
So we got, I got R20 minus things, so I know this is 4 times, so this is 4 times.
No, this is the same one.
0x 46.
You all get it together as an increment of 1. Where does R2 stop? It should be beyond this. Because it increments beyond this, right? And then where would that end?
Oh, yeah. Well, we'll get there.
Okay. And then also, how?
You're gonna add FF to 46.
+1 is just gonna be the next byte.
Yeah.
You say that overflows by.
You get to
I get it. It's 69 in decimal.
I just
One is
Trying to get ahead of which is right before
in decimal.
are setting that
So it's just like no, it'd be 60. 60. -1.
Loaded it in.
right? Like the fall is
Wait, no, that's wrong.
All right.
When you load the byte sign extent.
I think it's just gonna load all these bytes in TR.
Okay, well, anyways. Talk about this. Let's go here. What values did you guys get? What do you get for, what was my prompt? Let's see. R0. Okay. Good.
Yeah.
How about whatever it is, R2? -1? Otherwise known as FF? Okay. Good. Now we're getting a tricky part. We'll go through this. What'd you get for R4?
R2 shifted to the left twice.
I need a number. My brain can't do shifts.
20 plus 20 plus 12.
I can't do that. My brain don't do that.
69.
69? No, that's not what I got.
145.
It is 145. All right, so let's walk through this. Part 45. All right, so here's why. All right, so here's our program. C program registers are all empty, memory's empty. We're gonna compile. Push compile. I bet. All right, so here's a disassembled. Okay, so here we are. We've loaded, so the directives have been commented out. We have a label data. We have a byte. What's byte going to do? Byte's going to take the value hex 12 and place it in memory. And it's going to advance in memory. It's going to take the next value 20, place it in memory. It's going to advance in memory. And put the next value of hex 20 and then -1 in decimal. Okay? It's just a very simple, just whatever's in the comment, just going to put it down and go to the next comment and place it in. Any questions about byte? Okay. Where is it going to do that? So this is not obvious. You guys shouldn't necessarily have gotten it. But where is it going to place it? Because it has to place that somewhere in memory. If we go over to memory, here, and I can't. It placed it at memory location 8. Why? You didn't need it to solve the problem, you could have just taken it on faith, but it's gonna place it at 8, you can see it up there. And here we can see F, 20, 14, and 12. This is just how this particular IDE does it. And there's 2 whole bytes up there, or 2 words worth of data, and we put 8, we did space 8, which is not here. Let's see, space 8 did not make it through the compiler. Space 8 put those zeros. It said just basically 8 bytes worth to fill out, just to pad that space. Okay? That was not necessary, you could have taken it on faith. And so now we're gonna walk through, we're gonna do our move zeros from here. So we're just gonna clear out whatever values in there, move 0, maybe there's some leftover values. And now the trick here is that it's going to move in, because the compiler is gone and resolved the labels, the label was data, it's going to go to wherever that label is. It's gonna take the upper of 8, move it in. The lower of 8, sorry. And then it's gonna take the upper of data and put it in. So now, in R1 is the location in memory of the labeled data. And that is 8. Not necessarily the data itself. How do you feel about that? Some people are rioting. They're like, this guy's crazy. Yes?
Can you explain the space thing one more time?
Sure. So space is just a directive. You will not be tested on this. This is not like the most critical part. It's just part of this example to kind of move, the real goal for me to put it in is to move the data location away from 0, just so it had to be something. If we went and looked up, if you ever saw that, you can go look in the manual. Let's look here, where was it? I have no idea. Did I? Oh, space, my apologies. Space. That basically just fills up memory locations with zeros. All of this. It did it 8 times. 0, 0, 0, 0, 0, 0, 0, 0.
Like, so then where is it filling those zeros?
It started, well, the program starts, where does it start? The first thing it does is it puts down 0. So literally at memory location 0 in your hardware, it put a 0 down and it started incrementing. In fact, we can see that over here where address 0 has all zeros, address 4 has all zeros. How are we doing so far? Okay. Yes?
For the big endian or little endian, the value
Let's see, so
0
brain can't do it. Let's see. Memory is increasing downwards, right? So is the location increased with increasing? So numerical value increases with memory addresses. So we said the lowest value should be 12. So I guess this would be big Indian.
Is that the common case for, I'm assuming we're dealing with thumbs, right?
What's that?
We're dealing with thumbs, like the thumbs ISA?
Thumb can be big Indian, little Indian. It doesn't care.
What's the default?
There is.
I thought I read something about it being little Indian, that's why I was.
Yes, but this is not your cube IDE. Okay. Then, so whichever way you count, if you count memory address, what is that, 9 or 8, 9, 10, 11, you can count either way, but counting this way. Then, okay, so now we have that address, and we're gonna step through, step here. Now, 0, or R1 here has memory address 8, or has 8 in there, which is the address, memory address that will point to this. And we're gonna step through and we're going to add some things. Let's go through that. So we're gonna add R2 to R4 and place it into location 4. Oh, sorry, I loaded this. I'm gonna load the value of R1 and I'm gonna do post indexing. I'm gonna place it into R2. That gave me 9, or 12, I mean. And we're gonna step through, we're gonna add R2 to R4 and place that into R4. So I got 12. We're gonna go to the next, we're gonna compare. If we're not equal, we're gonna loop around. Okay. And we're gonna keep going. We're gonna go to the next memory location, add it in. Add it R0, compare, branch. We're gonna keep doing that until we're not equal. Do that 4 times, right? Yep. And then we're going to dead loop, which dead loop just stops execution. Any questions? Yeah.
If it's supposed to indexing, doesn't that mean that R2 is initially adding data, the a byte from data, like the name data? No. Like what's the first byte added from R2 to R4?
What's the first byte? It should have been 12, right?
But if it's supposed to indexing, wouldn't it start at the position that data's at or no?
Yeah. It takes that data and then it increments after that's done.
So it takes the first thing added would be the address of data or no?
When you're talking about load, you're talking about here, right? So it's going to go to it's going to use the address R1, whatever that address is. It's going to go to R1, it's going to grab some data. It's going to go put it into R2, and then it's going to increment R1 by 1.
And R1 starts the address of data, right?
Yeah.
So because it's incrementing after, wouldn't it add the address that data's in first or no?
We have because the line that data is on, it looks like it's its own address location, as opposed to it being where 12 is stored. I was confused about that too.
Sorry, say that loud.
It looks like data is its own label for its own address location, and 12 comes after it, but it's actually where 12 is stored, right?
Yes. In fact, you can see the addresses here are the locations. It's not its own line. It's just the label of where it would go.
So data is just a pointer to basically the address that those bytes are on.
Yes. So labels are just get resolved by your compiler to a memory location.
I see, okay.
Own line.
Now I got a different number than 145, so I'm like, I bet you know some math labs.
We can come back to it, or we can do it after class to see if we get through it, yeah?
It's 145 in hex, right? Which would be 325 in decimal.
Yes. It would be 25?
That tripped me up too, I was just wondering.
That makes sense.
Okay, you got that, okay, sorry, should have said that. Okay. All right, any final questions for this one?
Should I not be a negative number?
Not a negative number. Or
Technically shifting to the left, which is 0xf times ff times over. Shifting to the left twice.
we'll go through this later. You guys can put this in cube ID, play with it. This goal is not to be like, oh my gosh, be perfect. I'm not asking you to, in this class example, to be perfect. Just work through all those little steps, work through all those commands to understand what they do. That's the only goal here. Getting the answer is, like, you have to be perfect in every little thing. All right. Yes.
Wait, sorry, how did it jump to that?
I'm sorry?
Wait, how did it jump to that?
Because branch was not equal. The compare said that, let's see. The compare said that those things were, that those things were equal. The flag, branch not equal.
Okay. Oh.
All right. In the interest of time, we'll go forward unless there's any last questions. Any questions? Okay. All right. So we talked about, give you a little background to understand the GNU toolchain exists, right? About directives, labels, and went through an example. Now we'll talk about the application binary interface, which is an agreement between programmers about how we're going to structure function calls, essentially. How we're going to do subroutines with Callee Safe registers, and how we're going to do stacks and link registers. All right, I just said this is a contract. Basically, it's, you want and your buddies want to go and write functions in assembly, and you want to make sure that when you put stuff in registers that somebody else isn't going to clobber it. Interest of time, we'll move forward. So some API basic rules. So all subroutines must preserve R4 through R11 and the stack pointer, meaning that the main function can rely that those still exist. The arguments are passed through R0 and R3. So those lower 4 registers are how we're going to pass arguments through. If you need to do values that were larger, we'd have to use another functionality to get that done. But basically, those are predefined registers that you can do it. The return, when you return a function, you place the value in R0. You can use R0 and R1 for 64 bits. You could go all the way up to the first 4 registers if you want, but the convention is you start with the first element being returned in the lowest register. If you need that space, so say you're a function and you need more space, because you can't get everything you did in those low 4 registers, then you have to go and preserve the upper registers. You're gonna have to put that on a stack, do your calculations, pop it back, put it back on your registers when you're done, okay? So we'll go through some examples. This is the visual indicator. So these are, these would be, let's see, Callee Safe, and these are Callee Safe. It's not really that big a deal, but R9 is a specialty register. For the purposes of this class, you don't really have to worry about it. It's only in threaded operation, but you should preserve this register as well when you're writing a function. And R12 is used in interrupts and as a scratch space for different types of subroutine calls. We don't have to worry about that in this class either. So for now, you can just assume if you're a function, you get to use these variables and you have to preserve everything above. Okay. Just another graphic showing the ways in which you can do input and output data. So you got the first 4 registers as inputs, and you can use, technically you're only supposed, well, you can use the last 4 bits or 4 registers as outputs. But that's the convention of how ABI works. So let's walk through the example. So when I call a subroutine, let's see, a couple steps. First, you're going to want to branch to a label, so you're going to go somewhere. And here you're going to branch link register. So when you call a subroutine, you need to know where to come back to in your code. So you need to store that somewhere. So we use the link register, which is R14. And so here you're going to go and increment the link register, or the program counter by 4, which is the next command. And you're going to place that memory address into link register, and then you're going to set PC to the label, and that's the location you're going to go to. Any questions? Yeah.
Why do we do a PC plus 4?
Because you want the next command. Right now, when you're on PC, you're on your branch command. You are on BL label, right? That's the instruction that's being done. And you want, when you return from this branch instruction, you want to go to the next place in location in memory, the next command, which is always incremented by 4. Even if it's a 16-bit command, it's always incremented by 4.
As a programmer, we have no restrictions when we're using the registers, right? So like, let's assume I was like a bad programmer and I overwrote R14 after branching.
Yeah.
So meaning I have no return point. Like, I can do that, right? I mean, I shouldn't, but I can do it.
I mean, yes, the compiler will not stop you. Okay, you would violate the ABI contract, right? So yes. So you shouldn't do it.
But I can.
It'll be bad news bears, but you can.
Branch instruction can't be part of like a pair of 16-bit instructions, because then you would, like the +4 increment would.
Now as the good edge condition, I bet the assembler would look at this and say, okay, fine, I'm gonna make sure that we're not off by a half, right? That the branch instruction wasn't the top half of the 32-bit address. So yeah, you wouldn't happen. You guys don't have to worry about that. All right. Yeah, so let's walk through an example here. So this is just, we're gonna do sum of squares. So first you can see that R0 here is the first input to this function. We're gonna place that in R0. We're gonna go through R1 is the second input of the function, and we're gonna place that in R1, and then we're gonna return to R0. And then you can just see that we do 2 multiplies and an add to do this, okay? So in this example, we're going to go through, we're gonna move some things in, we're gonna call this function, and then the move R2 is just at the end, just to show the error condition if it could occur. It's not part of the function. We just need some place in memory to go to, okay? So this is where we're trying to bring all the things together. Here we have code. This is memory that contains our code, and I just, instead of putting the binary or hex in here, I just rewritten it so we know where we're going. We have a label here. So that label is been resolved to some memory address, and then we have our registers. We're gonna start with the PC counter pointing at 128, so that's the memory location. We're gonna execute that. So we've moved the immediate 3 into R1. or R0 I mean. Now we can see R0 has 3 in it. We're going to advance the PC. Now we're going to move 4 into R1. We're going to advance the PC. Now we're going to do our branch. We're going to branch setting up the link register to the label, which is SSQ. Okay, so first what we're going to do is we're going to grab the next instruction after the branch. We're going to put that in the link register, so that's where we go when we're done. So we remember where to go. And then we're going to increment the program counter to the address that is represented by the label SSQ. Now we're going to do that first instruction, which is multiply R0 times 0 and place it into R2. The next instruction after that, R1 times R1, place it in R3. Add those together, place the value into R0, and then we're going to branch to the register. So BX is branch, and then branch register, and which register is it? The link register. So we're basically going to take the value of the link register, put it into program counter, and then advance. And then we're just moved back to what that location was, which was the extra function we added to the example, move R2 to R0 to R2. Any questions?
Do again.
What's that?
Do again.
Multiply.
How does like function call within function call?
We're gonna do that next. All right. Feeling good? So a lot of this class is just knowing how code, and we're gonna have more advanced memory examples, but how does code, register, and memory work together? At least the first part of this class. All right. And then we went to end. Great. All right, so some caveats here. The PC, in my example here, the PC incremented by 2 or 4, if you follow closely, and the least significant digit of the LR was always 0. Okay, that's the nice sanitized version we give you. If you're ever gonna look through your disassembled code, you're gonna find that each time it always increments by 4. Okay, and so sometimes you're gonna have to put all zeros in for the edge conditions that we talked about. Sometimes the codes don't evenly align up. Let's see. And then because of that, we're going to have codes that are instructions that are 16-bit and 32-bit. Okay. If you look through your disassembled code, you'll find that the link register is always, the least significant bit is always 1. And that's just telling the core that these instructions are thumb. And it turns out the Cortex M family can only do thumb and thumb 2. Okay. So you're always going to see your link register is always 1, even though it only can increment by 4. Oh my gosh. But just these caveats, if you're looking in lab and you can't understand what's happening, those are the caveats. Any questions? Yeah.
It's like before you were walking through the code, we had the PC increment by 2 at like this particular place, like the move and the end. Is there a reason for it? Like how do we deduce that on our own, like when we are building that?
If we had gone through and put the hex in here, we could resolve that some of those instructions only need 16-bit while others need 32 bits. And so to make it easy, we just incremented by 2 for those cases. However, as I pointed out, the core would actually always increment by 4 and then just decide then if it's 2 16-bit or 1 32-bit instruction. Yeah.
In the case where loads into 16-bit instructions, and you'd fill the other one with the zeros, correct? How would it go back in, because I'm assuming you would need to run that other instruction at some point, how would it like?
So the edge condition that was brought up is, what happens if your branch, your next instruction was a 16-bit instruction, and branch was only a 16-bit instruction, and you're incrementing here, you're only pointing at the lowest, you can only pull in 4, right? And here was branch, what would be that next instruction? How would you address to it? And I'm gonna guess for that particular case, it would just fill in all zeros for there. The compiler is gonna see, oh, this is a no op, and then just go on to the next one. Does that answer your question?
Yeah.
It is a rare edge condition. I would not worry about it. The big takeaways are there are 16-bit and 32-bit instructions. The program counter increments by 4. It fetches, the full 32 bits and then decides if it's two 16 bits or one 32.
2 16 bits will run them and then increment by another 4, correct?
Yes. Yep. Okay. So let's talk about stacks. All right, so now we'll do, this is this example of a non-ABI compliant call. Maybe we should put the slide somewhere else, but just to highlight the issue if you don't do it well, right? If you go and clobber the upper registers, this wouldn't work. So here I'm gonna move 100 into 4, I'm gonna call foo. And here, you're gonna move 10 into R4, and then you're gonna branch back. Well, now if you add 1 to 4, you get 11, where you should have gotten 101, because this is a non-ABI compliant call. So just, you don't need to point that out, but if your stuff's not ABI compliant, bad things can happen. So here is one way around that error condition, which is if you really, and we didn't motivate why this foo needed to use R4, but let's just say it did. What are you supposed to do? Well, if you're gonna do this, you need to go and push the value in R4 onto the stack. Then you can use R4 for whatever you want. Then you need to pop R4 back, preserving the upper registers, and then you branch back, and now your program will execute properly. Okay? So this is the way we're gonna overcome the fact that we need extra space for our program, or scratch space, is we're gonna preserve, is the function's responsibility to preserve the data in the upper registers. Yeah?
And this push pop thing like gets the value to the stack register that we had allocated? Like,
yeah.
Okay.
We're gonna go through that just next.
So is push and pop a built-in command?
Okay, great, good. I went too fast. I should have prefaced this, clear the push, should have put the slides in a different order. Okay, so push. Push is a command, just like pop, that allows you to push things onto the stack. It keeps track, uses the stack pointer, which is one of the registers, I think R13, tells you where in the stack you are, and then it's going to take registers and store that up there. Interesting here is that stack doesn't have any order to it. So you could say push doesn't have any order to it. So you're saying push R6, R7, R8, those 3 registers, put those on the stack. It will do it in this order regardless of, even if you put the order the other way around. There's no order to this function, okay? Same with pop. So pop is just the opposite. It's gonna take things from the stack. It's gonna look at the stack pointer. It's gonna say, okay, go to this place in memory and put these things back into those registers defined. And then it's gonna keep decrementing or incrementing the stack pointer as required. So for an example, push here, if you're gonna take push and put R3, R1, R7, R2 in there, it's going to, it points at the last known piece of data, so then it's gonna put in R3, R1, R2. It's going to increment the stack pointer, I guess decrement, is gonna put 7, 3, 2, 1, and push is just the opposite. It's going to push values R3, R1, R2, R7, R2. Okay. Yes?
So does it like always sort whatever is in the parentheses?
Yes, you could do multiple pop instructions if you wanted to. Separate. Like pop R1 and then pop R7 and then pop R2, pop R3, but this would be a more compact way of doing it.
When you say it doesn't have order, kind of what he was saying. So if I push like R6, R7, R8, and then I were to pop and say R7, how does it like? Because I thought the whole point was that the stack pointer is pointing at the top, right? So if I'm only popping R7, wouldn't it have to move down, pop it, and then?
Well, that
seems like a lot of work.
But it doesn't keep track of that, right? You said put this data in order, and now I want this special one, and you're using the label R7. Well, the stack has no idea that when you pushed it up there, this was R7. It just it's just a memory location. So you as the programmer have to keep track of the order in which you put things up.
So the parameter when I'm doing pop, is just saying take the top and put it in that register.
Yes.
Okay. That makes more sense.
Yeah. So the question for you is in the hint. So why is pop and push order invariant? And then the hint is think about how you would design this instruction. You want to be able to take multiple registers, one line, and tell it, I want these number of registers up in memory. And how would you design that instruction, and why is it order invariant? Talk amongst yourselves.
Push multiple registers to the stack and
I don't think I'm still confused about, like, I had the same question that you had. So, if you push R6, R7, right, if you pop R8, pop R7.
because then you have to do some kind of priority selector. That was a major connection.
That register. So now when it'll just take whatever's at the top and put it in the register that you specify. So you could accidentally switch up 6 or 7 What's the push? You can push.
What do you think?
Separate.
You're like, I don't know. It's late in the day. This guy's been talking about bits too long.
Like normally when you load and store, most boring part. That solution they give you.
See, why is that?
Well, the compiler doesn't keep track, right? The stack pointer is the thing that tells you where you are in the stack. And so
ChatGPT, is this a good question?
You as a programmer have to keep track of that order.
I'm saying if you push multiple then you individually pop it. Right?
Correct.
I just rewrote the whole thing and we don't have this.
Nope, not really. But why is it? Okay. So what do you guys think? Why is push and pop invariant to order? Ooh, pretty much. Let's take a look. So if we go look at the encoding, it just says, hey, here is the register list. If you look at T1 encoding. So it goes, you put a 1 if you want to move the R0 register. I want to put a 1 in slot 1, so you could put the binary number 3 if you wanted R0 and R1 put up on the stack. So when your hardware is trying to decipher this code or this instruction, it doesn't have any order. It doesn't know which one you put in there. So it just has to choose the default order. Yeah.
Why can't, so okay, if I were to push 14 or 14.
Yeah.
Does the M become a 1? Is that what's going on?
Yeah, I suppose M would come. I'm sure there's a way. What's that? R14 is the link register. Yes. And we didn't. I'm sure there's more encodings that it did not show. But yeah.
What are the bits in parentheses?
Oh my gosh. Look, I can't know everything. This is. You know how big this manual is? It doesn't even fit on his laptop. I don't actually remember. I'm sure in the next page here where it talks about all the details, it probably says. Sorry. One last one, yeah.
So like, okay, forgot.
All right, so my general advice to you is if you're going to do a multi-register pop or push, or sorry, multi-register push, just do the exact multi-register pop. All right, just keep it simple. If you're going to want to access those things out of order, then just use a pop instruction with one register, and then you can go and keep track of it. But you have to keep track of what things on the stack are, so it's best to put it up in the order, or bring it down in the order that you put it up, okay? Yeah. Okay, so let's go through a multi-subroutine example. And so here we're going to take the cube of something. So we have a function quad. That quad function calls a function squared. Simple things, but just enough to watch how we deal with the link register and the stack. All right, so in this simple example, we're going to call that again, and then go back to main. All right, so here we have code. We have code in memory. We have the actual disassembled or assembled code, and then we have a memory address, okay, up there. So this is all unified memory, and here we're just showing the break, so we're showing that we're not in code space anymore, we're in the stack space. So our stack pointer is pointing up to that value doesn't matter. It just says this is where my stack pointer is, and that value was placed by somebody else, okay? Doesn't matter. And then we're program counters pointing to move R0, move 2 into R0. Okay, so first we're going to move 2 into R0, and then we're going to branch link to a label. So here we're going to go to the label quad and update the program counter. We're going to update it by 4 because we need to know where we're going to go back to. Then we're going to go to quad. So because quad is going to call a function, we need to preserve that link register, because if we don't, we won't know how to get back to main. So now we need to push the link register up into our stack. So we're going to push that. We're going to branch to square. So we're going to update our link register. Now that our link register got overwritten from what we would need to get back to main, so that's why it's up on the stack. We're going to do we're going to square something. We're going to branch to the link register, which is basically putting it in the program counter. That's the next BLSQ in the order. We're going to do the whole function again, put it in link register, put that into multiply R0 times R0, branch to the link register, and then, okay, so now we're done. We're leaving quad, right? We're going to exit quad. We need to figure out where we're going to go. So we need to go pop link register. So now 104 is going to be pushed into the link register. And then because we popped, we've increased the stack pointer to the next spot. Okay, we're giving back that space. Notice that this doesn't get destroyed, even though we don't care about the data in 1FC. It still exists, it's still there. Okay, it's just not used. And then we're going to go back, branch to register. What register? Link register, and that's going to bring us back to main. Simple example. Any questions? Yeah.
I'm just curious, if you wanted to never have to worry about which registers you're saving to the stack, can you just always do everything? And then, like, would that, like, if it was a test question to do an ABI compliant thing and just push every single register?
I'm going to make sure all mine say to do with efficient code. I mean, so if you look at your disassembled code, they are so protective. Like, they're doing frame pointers and stack pointers and all these things not to mess up. So it's not bad to be cautious, I guess.
Yeah, I remember my question. So what's the most number of registers you've seen used by one instruction?
The most number of registers?
Yeah, used by one instruction. Also, like
probably 3. Like, this thing plus this thing goes into that one. I don't know. And if somebody finds a bigger one, let us know.
Registers R0 through R3.
Yes.
Those ones, should we put on the stack before we do like a function call because they're caller?
Yes, if you as the main want to save that information, that's really important to you, then you have to put that on the stack.
But even if, so like, let's assume that I'm calling a function that only uses one parameter, right? So I have to make R0 be the parameter I want it to be and then go. I should, if I'm using R1 and R2, for other things, I should also.
You should, because unless you specifically know that you designed that program, you don't know what crazy things they're going to do.
But I don't do that for the rest of them because they're supposed to take care of it.
Exactly. Yep. So the main function, the program that's calling a function needs, if it wants, has to save the values in R3 through R0, and the function itself has to save everything else. Okay. Any other questions? All right. We still didn't get to an example. I don't know when we're going to get to it about moves and stores and loads, but oh well, we'll figure out a time. To recap, we did tool chain. Again, the biggest thing to know about the tool chain is there's a bigger world underneath there. You're going to take C and assembly and put it into your binary files. Oh, I forgot to say this. Your binary file is the thing, oh, I said it, goes into Flash. And your disassembled goes by your programmer. On your way out, leave your worksheets up here. And then we talked about binary application interface. All right, thanks.
Gonna miss out. I hear Chris is gonna cook today.
I was just told to.
Actually cooks, maybe okay.
Just hear
No worries, thank you.
hey.
He has an interview at Boston Dynamics. So there, and I'll be doing it alone. So I'm going to the lecture on Wednesday. How can I like not miss on participation, which like happens in the work?
How do you make up something you missed?
Yeah.
Yeah, I'm going to answer like a whole bunch of questions. Yep.
For 470,
Yeah.
it's unlimited. You just only can do it every 5 minutes. Lab.
Oh. Just work.
I'm so tired of hearing about this.